Okay, so you're telling me there's no rational number whose square is 2. But why does that proof with m over n really work? What is it actually using? It's using the idea that every rational number can be written in lowest terms, meaning m over n, where m and n share no common factor. That lowest terms condition is not decoration. It is the trap. If the fraction squared equals 2, then m squared equals 2n squared. The equation says m squared is even, because it equals 2 times something. Then m must be even, because only an even number has an even square. Writing m equals 2k forces n squared equals 2k squared, so n is even 2. So both m and n are divisible by 2, which contradicts that the fraction was reduced. The deep point is that parity behaves rigidly under squaring, and reduced form turns that rigidity into a contradiction. Fine. Then what's the deal with those sets a equals the rationals with p squared less than 2 and b equals the rationals with p squared greater than 2? Why is it such a big philosophical moment that a has no maximum and b has no minimum? Because it shows a structural gap in Q as an ordered set. The construction of Q equals P minus the quantity P squared minus 2 over P plus 2 is a theoretical maneuver. It manufactures a rational Q that is closer to the boundary defined by x squared equals 2 but stays on the same side. It proves no matter which rational P you pick with P squared less than 2, there is always a bigger rational still satisfying less than 2. So A has no top element. Similarly, B has no bottom element. That means the cut between square less than 2 and square greater than 2 is not realized by any rational. When you say no point in Q separates A from B, what does separates really mean? It means there is no rational raw such that every element of A is less than or equal to R and every element of B is greater than or equal to R, with R acting like a boundary. In R, that separator exists and is square root of 2. In Q, the boundary is missing even though the order still lets you talk about below and above. This is the completeness issue. Speaking of order, what is an ordered set in the pure theory sense? It is a set equipped with a relation less than that is trichotomous, meaning exactly 1 of x less than y, x equals y, or y less than x holds, and transitive. This is what allows consistent comparison. Once you have that, you can define boundedness. An upper bound is just an element that sits above everything in the subset. Then supremum and infimum are like best possible bounds, right? But why do we define them so carefully? Because maximum might not exist, yet at least upper bound might. The supremum is not required to be in the set E. It is characterized by 2 logical properties. It is an upper bound, and any smaller candidate fails to be an upper bound. That second clause is the key theoretical move. It encodes minimality without referencing distance or geometry. In Q, the set of rationals with p squared less than 2 has upper bounds, but no least upper bound inside Q. In R, it does. That difference is basically the definition of complete ordered field. So is that where field comes in? What role do the field axioms play here? They guarantee you can add, subtract, multiply, divide except by 0, and the operations behave associatively and commutatively with identities and inverses. The order structure and the field structure together let you compare numbers and do algebra while respecting the order. The missing piece in Q is not algebra, it is completeness. Not every non-empty bounded above set has a supremum. If completeness is the real dividing line, what changes when we build R from Q? Are we adding new numbers, or are we adding new limits? And if a set has no maximum, why do we still expect a supremum to exist at all?